Started. Okay.
Okay. Well, welcome everybody. My name is Andres Marty, and I work at Key Curriculum Press as a development editor. I spent 13 years in the classroom as a high school math teacher prior to my time here at Key, and I'm going to share a number of activities today that are sort of in preparation for Pi Day, various things to do with pi and circles. And to get started, I'm going to ask a couple of quick poll questions to get a little information about you all. So here is the first question. Which version of Sketchpad do you have? Sketchpad 5 being the one that's been out for the last year. Sketchpad 4 is the older version. And then a couple of other answers for those of you that aren't sure or if you don't have it. And it looks like about 90% of you have voted, so I'll give it 2 more seconds here, and then I'm going to close the poll.
Andres, can I just pop in for a second?
Sure.
Some people are sending their answer in the question panel. So when Andres puts a poll out, all you've got to do is actually select it right on the poll. You don't have to type that in the question panel.
Okay, thanks for clarifying that. And we got 92% here, so I'm going to go ahead and close the poll. And it looks like we got a fairly even split between those of you using Sketchpad 5 and Sketchpad 4. A few of you have something that you're not sure which version, and very few of you don't have Sketchpad at all. Hopefully I'll be able to convince you that Sketchpad 5 is totally worth the upgrade. Let me hide this real quick. And for those of you, if you're not sure if you have Sketchpad 5 or 4, Sketchpad, you can tell by just looking at the toolbar. In Sketchpad 5, you have a polygon tool, a marker tool, and an information tool, which are not part of the Sketchpad 4 toolbar. And that's how you can tell very quickly visually. Second question I have for all of you, just to get a sense for where people are, is which level that you teach at. Curious to see how many elementary versus middle school versus high school teachers we have. Looks like about 3/4 of you have already voted. And wow, okay, got a big poll turnout this time. I'll go ahead and close it. So we definitely have a majority of high school teachers, about 2/3 of you, but 1/4 of you are middle and elementary school teachers, which is, of course, a very appropriate level for talking about pi and circles. So thanks for that information. And so I'm going to get started by doing an activity that many of you might have already done in the classroom. And in fact, what I'm going to do is find out how many of you have by asking you one last poll question, which is, I'm curious how many of you have ever done an activity where you've actually brought in lids or circles of some kind and had your kids physically take measurements of those lids, measure the circumferences with string and measure the diameters, and then look at some ratios from that data. And it looks like over 90% of you have voted, so we'll take a look. And it looks like 3/4 of you have done such an activity and 1/4 of you have not. It is definitely something I did with my kids when I was a teacher. And let me close this. And it's a great activity with all of its inherent inaccuracies in measurement. But it still was pretty powerful, and the first activity we're going to look at today, whoops, is I need to start with a blank screen here, is to do a virtual version of essentially that same activity. So I'm going to start off by just creating a segment and constructing the midpoint of that segment, and then constructing a circle that goes from the midpoint to the radius point of the segment. Excuse me. And you can see now that I've basically constructed a circle with a diameter, which is dynamic. And now we're going to do what you would, same thing that you do with the physical activity, is we're going to make a couple of measurements here. So I am going to measure the length of the diameter, and I'm going to measure the circumference of the circle. I'm going to go ahead and use the text tool to change this label to diameter. And I see that the other one's already called the circumference, so I'll leave that alone. And these measurements are dynamic in the sense that when I drag these points of the circle with diameter that I constructed, you can see that the measurements update automatically. So as I change it, the measurements respond to their actual size. And what I want to do is I want to gather some of this data. And so one way you can do that in Sketchpad is you can select these two measurements and then go to Number, Tabulate. And this creates a table. And you can see as I change the values here, not only do they update here, but they're also updated in the table. But I want to be able to take, say, this data right now and keep it in the table. So I will double-click on the table, and that freezes that one value, adds a new row, which is now the dynamic row that's updating. So I'm just going to change this a few times. I'll double-click on it again. And I'm going to just gather a bunch of data for circles of different sizes, just like you would do with real lids of different sizes. So maybe a really big circle, and maybe a really tiny circle, and then a number in between. There are also ways you could automate. I could animate this and add table data, but I'm not going to make this more complicated than I need to. Point is, I just want to get a data for a bunch of different size circles. And now what I'm going to do is take this data and plot it. So I'm just going to make this a little bigger, give myself a little more room, maybe move this over here. And so I'm going to select the table and go to Plot Table Data. And it asks me what my choices for X and Y are. It's by default, diameter is the X variable and the circumference is Y, so I'll just stick with that. And you can see that it automatically plots this data. And at this point, if I were doing this with kids, we'd ask some questions and what do you notice about the data so far? And you might notice that it looks like it lies in a straight line. We could verify that it lies in a straight line by using a line, or say a ray in this case. And you kind of look at it and it kind of looks like no matter which point I pick, they all sort of seem to be lined up. But before I go that route, I kind of want to take this in a different way. So another thing you can do in Sketchpad is these points are now all statically plotted. They are all plotted based on what the values were that I captured in this table. I can change the axes and all that, but the points aren't going to move. But what I want to do now is choose the diameter and the circumference again, and this time I'm going to choose plot as XY. So this is going to plot a point XY, which is selected right here. You can barely tell how it's different from the rest of the points. So let me make this a little bigger, and then let me change the color of this point I just plotted so we can tell it apart from the other ones. I'm going to make it, I don't know, green. But it didn't turn green because I missed something. Let's try that again. Green. All right, so now we have that one green point. And this green point is the one that I just plotted. I'll make this a little smaller again so we can see all the old plots. And I just plotted it using the values, the dynamic values for the diameter and circumference. So if I change my circle, you'll see that this point moves. And it looks like maybe I had the wrong one selected before. I don't know where this one came from, but I'm going to make this one red again so I can tell it apart from the one that moves around. So you can see that one point moving around as the circle gets bigger and smaller. And what's really powerful about doing this is it really gets down to the concept of what a function plot is, which is a concept that students often miss. I know I myself, when I was in the classroom, would often teach kids how to graph a line using the y-intercept and the slope and so forth. And a lot of times by going through those techniques for graphing, you kind of lose sight of what it is that the function plot actually represents. That it represents all the possible inputs and output pairs generated by some kind of relationship. And we can really make this clear by taking this one point and tracing it. So I'm going to trace this point now, and as I drag my circle around, this green point starts leaving behind traces of itself in all the different places it's been. And I think this really kind of powerfully shows that this is really a representation of all the possible different size circles I could make. Which is what a function plot is. So anyway, that's an extension you can do on Sketchpad, which I really think is powerful. Now I'm going to go ahead and go back to using array, and I am going to start from the origin and go through my movable point here. And the array I'm making because it's an object I can select, and then I can measure properties of it. In this case, I want to measure the slope of this line. And so when you measure the slope of this line, it turns out to be 3.14. So similar to the activity that you do physically with students, you look at the ratio here of the circumference to the diameter of any circle, and you can see that it lies on this ray, on this line, that has a consistent slope. I'm going to go ahead and bring this out a couple more decimal places. So let me just change the properties of this measurement so that its value goes up to, say, 100 thousandths, and then we can see that it is the value of pi out to the 100 thousandths place. All right, so at this point, I'm going to move on to another activity. Curious if there's any questions that you'd like me to address right now, Karen?
The only one was about people who have version 4. They wanted to know if they could do the same activity. So if you could just kind of...
Yes.
Yeah.
Yeah, absolutely. You can I'm not 100% sure about every single thing I present today being something that can be done on 4, but certainly the vast majority of it you could do in Sketchpad 4. The things that the kinds of things that you can do in Sketchpad 5 involve using the marker tool. I'm not going to get into that too much. I do want to just show that one of the big advantages of Sketchpad 5 is that when you're doing some activity like this, you can use hot text. So you can say, we measured the circumference and I'm going to just go ahead and, well, first of all, I'm going to make this so that it's not bold and italics. I'll make it a little bigger. But I'm going to just click now on the circumference measurement and the diameter. I can hear somebody's typing. Is that you, Karen?
Yes, sorry.
And I'm not going to finish writing this whole thing. The point I want to make is that these things, we could even add in here, which is this segment AB. And in this hot text, not only, there's two ways this works. One is, when I roll over something, like if I roll over, I got to go back to the pointer tool. If I roll over AB, it highlights in the hot text, and it also highlights in the actual diagram. And same thing with the measurements. So these things are linked dynamically to the objects that they represent, but also, if I end up changing something, like let's say we end up changing A out here to, I don't know, let's just pick P, it will update automatically here as well in the hot text. So those are some things that you can do with Sketchpad 5 that you can't do with 4, but the essence of this particular activity you can totally do with Sketchpad 4. All right, another quick poll. I'm curious to find out how many of you know about the Learning Center, the Sketchpad Learning Center that is part of Sketchpad 5. And we got about 2/3 of you voting. Wait till it gets up to over 90%. And it looks like we are just about there. So I'm going to go ahead and close the poll. And so 71% of you do not know about the Learning Center, which is really helpful to know because I definitely want to spend a couple of minutes letting you know about the Learning Center. So let's talk about the Learning Center. When you're in Sketchpad, when you open Sketchpad, you can link to the Learning Center from the splash screen, or you can get there once you're in Sketchpad by going to the Help menu, and the first part of it is all about the Learning Center. The Learning Center is a resource that we put a tremendous amount of time and energy and expertise into in order to support people who are new to Sketchpad. And so I want you to know about it because it is something that is actually built into the software. It's not even online. When you download Sketchpad 5, the Learning Center comes with it. And all you need to do is access it to get to all of this information that's in here. It has 3 sections. On the first section, there are some videos, interviews of students and teachers, as well as sort of the big picture from the designers. But really, these 2 sections, the using Sketchpad and the teaching with Sketchpad, have tons of resources that are super useful. So for example, in the using Sketchpad, there are the Getting Started tutorials. And these are 12 tutorials that lead you through how to use Sketchpad while at the same time doing some interesting mathematical explorations. And in fact, the perimeter and area tutorial, for example, is one that's very similar to what I just did for you in this activity here. The difference being that in this tutorial, when you select, it takes the approach of just selecting the circle and measuring the radius rather than the diameter. And so everything else is the same, but when you do this activity, since you're using the radius rather than diameter, you end up with a slope which is 6.28. It is basically a slope of 2 pi rather than pi. But more importantly, this is just one example of a tutorial. Each of these tutorials also, they include step-by-step instructions and embedded videos. And so depending on your learning style, if you want more. So, you know, you have, and I should say that in order to see the videos, you do need to be connected online. But other than that, everything is there. So you have the tutorials. You also have these Sketchpad tips that are organized by menu. So, you know, let's just say we were just doing this and I didn't know how to use the text tool. You know, I could look at the text tool and we have these one-page comic strip format text tips, Sketchpad tips that are really designed for younger students, but they really work great for students of all ages as well as adults because it encapsulates the information in a visual way and in a very brief way. And then on top of that, for each of these things, there are also videos that will lead you through how to use it. So anyway, that's just, and then there's links out to a couple of other, the Reference Center is more of a traditional help system as well as Online Resource Center. The Teaching with Sketchpad has lots of different sections, including videos about using Sketchpad at different grade levels and more information. It also has a lot of sample activities, so for every different level you can look at 10 sample activities. You can download the entire activity, which includes the student worksheet, the activity notes, the sketches, and it's all in a zip file. So, you know, when you get a chance, take a look at all of the things that are already there as part of the software. I was surprised yesterday, no longer so surprised today by these poll results. It surprises me that even though half of you use Sketchpad 5, only a quarter of you know about the Learning Center. So definitely a resource you want to take advantage of. It'll link out to some other things. One of the things it links out to is Lesson Link, and I bring up Lesson Link because it's a library of over 500 activities, and in preparing for this presentation, I went to Lesson Link and did a search, and if you come into keypress.com and you go to Key Online, you can then get to Lesson Link, and Lesson Link looks like this, and you can do searches and so forth. So I did a search on circles, and I came up with a bunch of activities, and this really formed the basis for some of the stuff I'm going to show you now. And the interesting that happened to me as I did this is I came across all these activities that had to do with radians. And at first I was thinking, well, radians, that's the kind of stuff you do in Algebra 2 and pre-calculus. It's really not relevant to just talking about the kind of diameter to circumference to diameter ratio. But I kind of had my own little aha moment as I started looking at some of these sketches. And let's take a look at this one for a second. I'm going to click on this action button, 1 radian, and see what happens here. All right, let's hide this and reset and do it again. So take a look. You have a radius here on a circle, and when I click this button, that radius kind of pivots around point B and then starts rolling along the outside of the circle. And so the distance this has traveled is 1 radius. So I'm going to do it one more time. This time I'm going to click on Show Arc. So I'm going to reset, Show Arc, and do 1 radian. You'll see that as it's rolling along the circle, it's going to trace out this green path of 1 radius length. And if I go semicircle, now it'll do another one, and a third one, and a little bit more. So now this has been 3 radii plus a little bit more to get to a half circle. I'm going to reset it, and this time I'm also going to say Show Ticks, and go the semicircle again, and you'll see that it's going to leave a little red tick mark. So there's 1 radius, and there's a second radius, and there's a third one, plus a little bit more. But if I do the whole circle, I'll get a 4th one, a 5th one, a 6th one, and then a little bit more. So you can see here that we've gone 1, 2, 3, 4, 5, 6 point something radiuses to get around the circle. And like I was saying earlier, for me, the sort of realization that when you're talking about radians, that it's really completely the same thing as the circumference of a circle. Like, for me, they were sort of divided into 2 different categories of topics. But when we talk about the circumference being, we're using here, this is pi times the radius gets you halfway, and then 2 pi times the radius gets you the whole way. And it's really you can see it a lot more as these radii being wrapped around the circle. So it's just sort of, a different way of thinking of the same thing. Rather than just the ratio of the circumference to the diameter, it's also how many of these radii, or diameters as the case may be, can you wrap around the circle. So go one other somewhat related activity, but it's very similar. Here you have this balloon that goes up and down, and you'll see that what the focus here is much more now on the half circle rather than the full circle, right? So usually, like in this first activity that we did, we were looking at how many diameters are in a circumference, but here we're just taking a look at a half of the circumference, a half circle, and as the balloon goes up, this part of the arc gets straightened out and goes straight up. So I'm going to change the radius and do it again, and you'll see that this time it goes up much farther, which sort of makes sense, right? I just made this thing bigger. So as I make the radius bigger, I'm also making this half circle bigger. And so when I go up, it's going to be proportional to that radius. And you can already kind of see from this point that we have sort of a proportional relationship going on here. The bigger the radius, the longer this half circle when it's straightened out. But, oops, got too much going on here. So what we're going to do now is, let's see, we're going to do this again. We're going to add one more element to it this time. Once it gets to the top, we now have these measurements. So now I have a radius of 2.3, and the arc length that was swept is 7.23. And like before, I'm going to go ahead and tabulate this data and add it to my table. Let's go down and pick a different size circle. So I'll make a little bigger one, go up. Tabulate that data again, go down, and I'll just do one more, a small one. And I think it's enough for now for people to get the idea. But we'll go up here, tabulate that data, and let's go ahead and plot that table data. And again, we can see that it looks like we're getting a straight line here, and if I connect these and measure that slope, again, I get pi, and you might notice that in the last few digits here, it's no longer quite as precise, and that's because each of these measurements has a little bit of is rounded off to the last digit, and so therefore by the time you get out to those last decimal places, a little bit of error creeps in. But you can see again that pi comes up in this ratio. Now, what was really interesting to me in reviewing these activities is the different formats that we think of the circumference formula. And we're used to saying that the circumference is equal to 2 times pi times the radius, and but there's other ways to think of it. You know, another way is that I guess we usually use a capital C, so I'll use a capital C. The circumference is equal to pi times the diameter. And you know, in the first activity that we did, this is really kind of the formula, you know, that we came up with as we were looking at that relationship. But what I find really interesting about this activity is you're really kind of looking at a slightly different scenario. We're just looking at half a circle here. So really, we're looking at 1/2 the circumference, and 1/2 the circumference ends up is equal to pi times the radius. So what's interesting to me is that, you know, you can talk about the symbolic manipulation it takes to move between these different forms, the algebra involved, and you can easily get from these one to another, and you can substitute in 2r for d and change these things around. But each of these formulas, even though they have equivalent, you know, what they can all be converted into each other, they all kind of represent really different geometries. And for example, the geometry of this situation is really this formula, that half the circumference is equal to pi times the radius, which is a little bit of a different take than the first activity we did, where we were looking at the circumference being equal to pi times the diameter. Anyway, I found that interesting, and before we go on to the last part of this section, because we're going to move into area in just a second, but I have another poll question for you, which is which of the following values of pi, which approximate values of pi have you used in your teaching? So choices there. And this one, you can select more than one. So select all that you've used in the past. And we got 3/4 of you having voted. Give you a few more seconds here. Okay, I'm going to go ahead and close the poll, and it looks like we have roughly equal amounts of 3.14 and the more precise value of pi that you have in your calculators. And then a good 58% of you have used the 22/7. For me, it's interesting. Some people are very familiar with the 22/7 value as an approximation for pi, and other people have never heard of it. But we're going to take a look at this right now from a completely different point of view. So here is a sketch where, let me click this button and then you'll see what's happening. When I click this button, 2 points are going to start moving simultaneously. So you have point A that is sliding back and forth. It's just going along the radius in one direction, and point B is going around the edge of the circle. So let's take a look at that again so you can see what's going on. So B is going around the edge of the circle at the same time that A is traveling along the radius, and they travel at exactly the same speed. So A is traveling along the radius at the same speed that B is traveling around the outside of the circle. And so again, this kind of gets back to what we were just looking at a minute ago, what this really comes out to. This is 1 radian. This is 1 radius length, the length of 1 radius as measured along this arc. I do want to caution you real quick before we go on that this point A was traced. Let me show that one more time. A is being traced as it moves. But the trace of A is not the distance A traveled. It's kind of a two-dimensional path that's both determined by its linear motion along the radius and the circular motion by the end of the radius around the circle. So this path is in fact longer than a radius. But the distance that A traveled was literally just along the radius as the radius moved. So it's traveled one radii so far. All right, so let's take a look at one that doesn't stop right there. I'm going to animate this, and I'm going to try to stop it when it gets back to the middle. Bang. Okay, pretty close. So at this point, how far has A traveled? Well, it traveled along the radius and back again. So that would be one diameter, or 2 radii. And this B would have also traveled at this point 2 radii or 2 radians along the edge of the circle. All right, we're going to keep on going from there, and let's see what happens when we go once around the circle. So it's kind of producing this cool-looking graph, and I notice that it looks like it made 3 leaves. I'm going to call them leaves. Each leaf represents a diameter's worth of distance traveled by point A. And it looks like there's 3 of them, but it's a little bit more than 3 because there's this little part here that A has already started traveling on the way back. So let's see what happens if we keep going. And we're now on our second trip around the circle, and I'm going to just keep letting this run. And I'm going to keep letting it run until this thing gets more or less filled in. And this totally reminds me of my childhood playing with spirographs. If any of you remember those sort of geared wheels that fit inside of each other, and you would just keep going around and around and get some really interesting pattern that would fill in. So I've been talking too much, and I'm losing track of which trip we are around the circle, but I believe this is the 4th trip around the circle so far. And we're about to start our 5th trip around the circle, and it's slowly filling in. Again, I find this visually appealing, but the mathematics behind it is fascinating, which we're going to get to very soon once we're done here. We're now on our 6th trip around the outside of the circle, and it looks like we're getting close to getting back to where we started. We have one last rotation, so this will be the 7th journey around the circle, and it looks like it's going to be pretty much done after 7 trips around the circle. I'm going to see if I can stop it right at the right time. I probably won't be able to, but pretty close. All right.
Andres, can I interrupt because it's come up a couple times? What is point A? Like, how would you define point A?
Point A is a point that is on the radius that travels back and forth along the radius from one endpoint to the other endpoint.
So it's just a point. It has no, it's not the center point. Okay.
It's not the center. It's a point.
Andres, do you want to show the animation button, maybe? If you open it, will it show how the animation is defined?
Okay, so if you look at the animate button, it says point A is being animated bidirectionally along segment 1 at medium speed. So this is segment 1, and point A is just a point on that segment going bilaterally, which means when it hits one endpoint, it goes the other way again. And then point B is going counterclockwise around the circle. All right, back to this design. Let's take a look at how many leaves got formed. I'm going to count them starting from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 22 leaves were formed. And it took us 7 trips around the circle to get there. And there you have that 22/7 value for pi, which is just, to me, is just super cool. The reason, if you want to make sense of that, what's happened here is we've traveled 22 diameters, and 22 diameters is the same distance because the points are moving at the same speed as 7 circumferences, and when you divide both sides by 7, you're finding that the circumference is equal to 22/7 diameters. I just love that activity because pi comes in this activity out of nowhere, and what I really like about it is this value 22/7. Now this is not an exact value. 22/7 is a little bit too high, just like 3.14. It's a little bit too low. It's hard to tell, but when you get right to that start point here, there's a tiny bit of error. It's already started back again, but it's hard to tell at this level of precision that there's a little bit of error there. Okay, I'm ready to completely switch gears into area. Is there any questions at this point, Karen, from anybody you'd like me to address? Or can we start with the
There's
area?
just some confusion about what point A actually is representing and what that distance is representing, but
okay, here's a circle, here's a radius. I can construct a point on that radius. That point can go back and forth along the radius, but it can't go off the radius. That's what point A is. Point A is a point on the radius that has been set up to go back and forth, and that's all it is. So every time it goes back and forth, it's traveled 1 diameter. I don't know if I can explain it any better than that.
okay.
But it's a point on the radius that's going back and forth along the radius. That's what point A is. All right. It's already said. Okay. Let's move on to area. Quick question. How many of you have done this? So another activity that I'll get your vote on, an activity where you have your students take a circle and cut it up into slices, and then you can rearrange those slices kind of going back and forth zigzag-like to create a quote-unquote parallelogram. It's not exactly a parallelogram, but we got most of you have almost voted. Give you like 3 more seconds, and then I'll close the poll. And let's close the poll. So it looks like a majority of you have done this kind of activity, which is great. I always found it to be a pretty powerful activity. Some of you have not. So if you have not done the physical analog of this activity, you'll at least see the virtual one. One thing that's nice about the virtual one is that it is a little more precise, shall we say. When I had kids do this with paper and pencil, it was really hard to get all those little slices to actually line up right. They were using glue and tape and trying to get things to fit. And it was a little hard to get the precision. Here what you have is a circle. It's been sliced into 4 pieces, and these 4 pieces have been rearranged so that the 2 light blue ones are here and the 2 purple ones are here. And this doesn't look a whole lot like a parallelogram. But as you increase the number of sectors, so now we're up to 6, and now we're up to 8, and you can see the more sectors that are created, the better this approximation becomes. Because back when we were at 4, you had tons of the circle that was outside of the parallelogram. And the radius of the circle was in fact a lot longer than the actual height of the parallelogram, which only goes to here. But as you increase the number, these things start to converge. And so now, even with just 12 slices, you can already see there's not a whole lot of the circle that's hanging outside of the bounds of the parallelogram anymore. A little bit, but not so much. And also, the height of the parallelogram is now almost exactly the same as the radius of the circle. They're just off by a little bit. And you can see that the farther you go, the better this approximation becomes. So here at the limit of this model, where we're at 18 sectors, you now have all pretty good fit here, where the height and of the parallelogram seems to be just about the same as the radius of the circle, and the base of the parallelogram. Well, let's think about the base of the parallelogram. The height of the parallelogram is the same as a radius, so I've already put this here. That's the height of the parallelogram. It's one radius of the circle. And the base is equal to, well, it's half of the circumference, okay? If you take a look at just the light blue ones, well, if you take all of these edges along the light blue, and we're kind of pretending now that they form this straight edge, which they don't really, but the larger the number, the straighter it appears, and it is approximately equal to half of the circumference of the circle. So rather than 2 pi r, we have pi r, and if you multiply the base times the height of the parallelogram, you get the area of the parallelogram, so you get pi r squared. So that's one model for the area of a circle. Now, a colleague of ours, Scott Steckety, the other day, he teaches a methods class for teaching a credential program. One of his students wanted to ask more about this, so he created this, this model, which I want to share with you because it's so awesome. And this will be part of the sketch that you guys can get. So if I just click this Unroll and Fit Arcs button, this action button will take these pieces and it will then move them and create the same relatively sloppy looking parallelogram at this point. Let's unroll it for a second. Oops, wrong button. Press this button. But the difference is, or here, is that you have this parameter that you can now select and change to create more divisions. So if I increase, press the wrong button there. If I press the plus key on my keyboard, now it's 2, 3, 4, 5, 6. I'll go up here to 7 and see how it looks now. And you can already see that the more you slice this, the more it's starting to look like a parallelogram. And what's really cool now is I'm just going to leave it in this position, and I'm just going to keep increasing the number of slices. And as you can see, as this thing goes up, I'm up to, this thing becomes more and more, in fact, rectangular. As the slices get so small, it actually looks, you know, it's a parallelogram, but really, now the slices are so small, we might as well just consider it a rectangle. And just as before, you know, we have dimensions here of the radius, and then half the semicircle along here, pi times the radius. So that was cool, but then Scott also shared this other one, and this is something I've never seen before. I've never heard of this Archimedean circle dissection, but it's really, really cool. So here's the idea. Here you have the circle, and let's just consider the circle made up of like these strings that wrap around. And we can cut all of these strings along one radius and then unroll all of the strings. So here we see it unrolled. All right, let's take a look at that again. Let's roll it up again. And I want you to notice, first of all, that over along this dimension, this is going to be the length of the radius. And the longest string rolling out is the one that goes all the way around the outside of the circle, so that would have a length of 2 pi r. So when you unroll this circle, we end up with this shape that looks very triangular, that has a height of r and a base of 2 pi r. But again, we can increase the number of strings here, and so I'm going to select this parameter and start increasing the number, and you can see that as I increase the number of strings, this thing starts to look more and more like a perfect triangle. And again, so at this point already, you can't really tell they're strings anymore. It just looks like a triangle whose area is 1/2 the base times height, and if you take 1/2 of r times 2 pi r, you end up with pi r squared again. So a whole nother model for explaining why the area of a circle is pi r squared that involves just unrolling a circle, so to speak. Anyway, I thought that was, I'd never seen anything like that. I think that's pretty cool.
Andre,
right.
Can I interrupt?
Sure.
There's a question. Is that a right triangle? I believe it is, right?
Well, by the time you, yes, because you unroll these strings so that they become a right triangle, if that makes sense.
Before you move on, can you just quickly explain, there's been a couple questions about, you know, the animation and if do they have had to recreate these sketches. Can you explain whatever.
Yeah. Well, this sketch in particular involves some complex animations that I'm not even sure I could pull off, at least not without a lot of thought and time. So we're presenting these to you as part of this webinar. You'll be able to get the sketch I'm using, and it includes all these pages. And so this is an example of the kind of activity where you can use it just as it is. Someone else has already built it, and you can, you know, it would be, this in particular would be a tough model to build from scratch.
Correct.
Now, other things you can build pretty easily from scratch, and so that's a little bit beyond the purview of what I'm going to get to in today's webinar.
I think actually some people just wanted to know, are they going to get the sketch? And so just to re-emphasize for everyone, all the sketches Andres is using today, you are going to be able to get a copy of. In a couple days, I post both the recording and a zip file of all these sketches for you to download from our website, and you'll get an email that has the link of where to go get those. So you will get all these sketches with the animations. All you got to do is push them just like Andres is doing. So you will all get these activities afterwards.
Okay. I'm going to show one more activity, which is something that I used to do with my students. You know, like I said, this was new to me. I did used to use this other type of approach, this approach with my students, but but I found it to be still, you know, it's a little cryptic. It's kind of weird. This whole pi r squared. Yeah, you get r on one dimension. Let me show what I'm talking about. You get this radius here with this idea of pi r, and then you get pi r squared. Still seemed very symbolic. And so here's something that I used to do that I found to be kind of more viscerally satisfying, which is simply this. All right, I'm going to create a circle, and I'm not going to get into the details of how to create a custom tool. If you're interested, really, like I mentioned earlier, if you go to the Learning Center, you know, all of the stuff you can learn to do yourself by just doing the Getting Started tutorials. The first couple of tutorials are all about constructing shapes using geometric properties. But just as a whirlwind, I'm going to construct a square here using perpendicular lines. I'm going to use a circle to create two sides that are of equal length and put a point there. And then I'm going to construct a perpendicular from there to get the last vertex. I'm going to use the polygon tool and click on these vertices in order to create a square. And then I'm just going to hide the stuff that I don't really need to see anymore. So I've constructed a square, and now I'm going to create a custom tool out of the square. I select the square, I go to Create New Tool, and now I can create a new tool called, you know, My Square, or whatever you want to call it. And once you've created a custom tool, you can use it. So now I've created this tool called My Square, and when I select it, it will create squares. So I'm creating a square off of that radius, and then I'm going to go over here and create another square. And I'm going to create 4 squares that cover up the circle and a little bit more. So here you can see that we have 4 squares. And just to keep things simple for a second, let's just say that the radius is 1. If the radius is 1, then this square is a 1 by 1 square, so it's 1 square unit. And all the purple squares together are 4 square units. But you can tell that the circle is less than that, because this is not part of the circle on all 4 corners. So, just real quick, what would you estimate? If the square's area is 4, what do you think the circle's area would be? Again, this is an estimate question. So I'm going to look for you guys to answer this. Choices there are sort of going, you know, is it 3 3/4 and above? Is it 3 1/2 to 3 3/4? 3 1/4 to 3 1/2? 3 to 3 1/4? Or less than 3? And we got 3/4 of you have voted. Okay, and then see if we get any more votes here. I'll give you like 5 more seconds, and then we'll close the poll. And again, the idea here isn't Here I'm really doing something that I'm modeling what I would do with my students, because you can't really tell just from your estimating from this diagram. But I would expect to get something similar to this. So there'll be a small number of people who might think it's over 3 3/4, and a small number of people that might think it's less than 3. But you're going to kind of this leads to a good discussion of what it is. I always found that students were pretty happy to say that it's definitely between 3 and 4. It's clearly less than 4. It's clearly visually more than 3. Maybe that's not so clear. But what it turns out to be is that the area of the circle is in fact 3.14 of these squares. And even though that doesn't give a reason for why it's pi r squared, it gives a visual reference point. It's like, okay, that made sense to my students. It's somewhere between 3 and 4. And so this idea of pi r squareds is kind of like, well, it's not 4r squareds, but it's more than 3r squareds. It's in fact pi r squareds. All right, just a different idea. And then since I only have less than 10 minutes, and I have way more than 10 minutes worth of material, so let's decide what to do next. I have 3 more topics I could potentially cover. I would like you to have a say in which of those I go into. So you can look at limits of regular polygon area and how that relates to circle area. Look at the equation of a circle, and then also how that relates to the equation of an ellipse, and then looking at some models about cones and cylinders. And we got about 3/4 of you. And I'm going to cut it off here in 3 more seconds. So if you have an opinion, vote now. And it looks like we have a clear winner. So we will go that route. So you want to look at cones and cylinders. And that's what we'll do. So just so you know, all of the stuff will be on the sketch that you get with this workshop, even the things I don't get a chance to cover today. This is really this idea of a polygon, and as it becomes more and more sides, it becomes closer and closer to a circle. And this kind of leads you through that model, so I'm not going to talk about that one. And then there's a couple of pages about equation of a circle and sort of conics, but this is what you asked for. So let's look at these. So this is a model that is a 3-dimensional representation of a prism, as well as its 2-dimensional net. And this model is pretty cool in that you have controls for the representations. I can change the pitch of this 3D object by using the pitch control. I can roll it using the roll control, and then I can spin it using the spin control. So you kind of get this, you can tell that's a 3-dimensional object. And then here you see its net. But the net also allows you to change other measurements by dragging points. So if I want to make this thing taller, I can change the height just by dragging this point, so I can make it shorter or taller. I can change the radius of the base by dragging R. But then the coolest thing of all is I can change the number of sides by dragging N. So I can make it a triangular prism, rectangular prism, pentagonal prism, and so forth. And without going into all the details of this activity, this activity is primarily designed to break down a 3-dimensional object into its 2-dimensional net for the purpose of finding its surface area. But the thing that's interesting to me is, and this really gets back to part of the presentation I skipped, so let me just go back here for a second. Kind of an important concept here, right, is that when you're looking at the area of a regular polygon, you can break it up into these triangles. And when you break it up into these triangles, each triangle has a height and a base. But the base of this triangle plus the base of this triangle plus the base of every other triangle ends up being the perimeter of the polygon. So when you look at the formulas for the total area of this regular polygon, rather than looking at it in terms of each individual side length, you can look at it in terms of the full perimeter. And as the sides become more, the length here becomes the radius. Again, at the limit, the height of the triangle is the same as the radius at the theoretical limit. And at the theoretical limit, you look more and more like a circle, where the perimeter of the circle is now, at its limit, the circumference of that circle. So that same idea plays itself out in 3 dimensions. If you look at this model now, here we have these hexagonal bases, and then they can become 7-gons and octagons and so on. But the farther you go out, the more and more you realize that really a cone is just the limit of a prism as the number of sides goes to infinity. And it's a pretty cool connection there. So that's why when you get to the formula for, say, the surface area of a cone, you end up with this circumference of the circle playing a role. And the pyramid model is the same idea. Again, you have the same kind of controls in this model, and you have the same controls as far as the height and the size of the base and the number of sides. But it's the same idea. It's a limit again. So as you increase the number of sides on a pyramid, the base becomes a circle, and the shape becomes a cone. So a cone is really just the limit of a cylinder. Let me get my names right. This cone is the limit of a pyramid with the size increasing to infinity, while a cylinder is the limit of a prism as the number of sides go to infinity. All right, I was hoping to get to this other stuff, but I am out of time, and you can explore these things on your own. At this point, so I'll take any questions that have come up.
There haven't been a lot of questions, so you're doing great.
All right, well, since there's no questions, I'm just going to say that the cool thing about a circle is the connection between the equation of a circle and the Pythagorean theorem, and you can see that a point on the circle can be represented with a right triangle, and so you get that equation of x squared plus y squared equals hypotenuse squared, which is the radius, right? So this square here would be x squared plus y squared equals 5 squared. But if you take that equation, I'm not going to write it because I don't have time, but if you take x squared plus y squared equals 25, and you divide everything by 25, you get this. You get x squared over 25 plus y squared over 25 equals 1. Same exact circle, but now you can start playing with these two values here, which represent sort of the horizontal and vertical scale factors. And it's pretty cool if I just say change this from 25 to 9. You see that you get an ellipse. And while the dilation still goes out to 5 this way now, it only goes out to 3 this way. And just another cool thing that kind of connects circles to the larger body of things it belongs to, which is all of the conics. Certainly there's one other really cool activity that comes with Sketchpad in the Learning Center that you can check it on your own. It's called, where is it? No, it's under pre-calculus, I think. Under pre-calc, there's this patty paper parabolas, as well as analytic conics, some activities that sort of let you play with that idea of looking at conics as a unified group, rather than a circle being one thing and an ellipse being something else, and so forth. But that really goes away from pi, so let's bring it back to pi, and hopefully, is there any other questions that have come up?
I think not, but I think we need to wrap it up and maybe just emphasize where they can go to get ideas and ask questions, the Sketch Exchange and that type of stuff.
Sure.
Do you want to show them?
I'll show them that. There's also one last page here, another thing from Scott, which I'm not even going to talk about, but have fun with this. It's pretty cool. It's all about showing pi as sinusoids. But where to get more information? So when you'll get an email that will tell you where you can download the sketch that I used today. But when you go to Key Curriculum Press, and if we have some, and you go to Key Online, you'll find that we have some services. In addition to the stuff I mentioned before, the one thing I'll mention right now is a Sketchpad Sketch Exchange. This is a free service, so this does not we don't charge anything for this. It is a teacher-to-teacher exchange Teachers can upload sketches they've created, and you can go and download other teachers' sketches as well as participate in discussion forums. And it is a place to share with other teachers, and it is free of charge. As for other services like Lesson Link or whatever, you can go to keypress.com and look into that. And I believe that's it. Anything else?
Just a reminder to, well, first of all, thank you to everyone for joining us, and thank you, Andres, for this great presentation, and thanks, Elizabeth, for helping with all the questions. Just a reminder to everyone, we are recording the webinar, and it takes me about 2 days to get it up and posted along with the zip file of the sketch that Andres used and some of the PDFs that maybe go with it. So that will be up hopefully by Friday, so kind of look for that there, and it's at our website, keypress.com/webinars, and you just look under the archives for this one. You will also see previous webinars that we have done where we also have recordings and the archived sketches. So for those of you who teach other subjects, we have elementary archives, we have geometry, calculus, so there's a lot of those already there for you. So that will be up hopefully by Friday, maybe Monday, it depends how things go. Another reminder that there was a question here about how does Sketchpad Lesson Link differ from the Learning Center. The Learning Center is basically, Andres, how would you describe it? It's a huge resource.
The Learning Center is a phenomenal resource of support that's built into the software. It's part of the software. It comes with the software, and if you already have Sketchpad 5, you already have the Learning Center. You just need to know that it's there and start making use of it. Sketchpad Lesson Link is a subscription service that is separate from Sketchpad, and it is a library of 500 Sketchpad activities, and that are, they're sorted by content strand, by textbook, by standards. You can, if you have a certain book that you use, you can go specifically to lesson 7-3, and you can see which of our Sketchpad activities correlate to that particular lesson. But this is a separate service that is a subscription service.
And some of the activities actually all the activities that are in the Learning Center came from Sketchpad Lesson Link. It's just a small sampling of those. There's also a question here. I just want to make sure I address. All of you who have attended today will receive an email, usually that comes by tomorrow, with a PDF of a certificate of PD credit hours for attending today. So that will be coming to you in a follow-up email. So you should probably get that tomorrow. And if there's no other questions, I'm just making sure I'm going down the list right now. If there's no other questions, we are going to say goodnight. Thank you again for joining us. We'll stay on a little bit longer just to make sure we get all the questions answered. And but if not, thank you for joining us. Have a lovely evening. Thank you again, Andres and Elizabeth.
Thank you.
I'm just going to answer a question if anyone's still online. If they upgrade to 5, can you still save your sketches in level 4? Yes.
Yeah, you can.
Yeah. You can save Sketchpad 5 down to level 4, but you do lose the functionality of 5. And you can open a Sketchpad 4 in Sketchpad 5 as well. But you cannot open a Sketchpad 5 in Sketchpad 4, correct?
Unless you save it specially
Unless you
as a
save
4.
it as a 4, right.
But if you normally save it as a 5, because 5, yeah, there's a lot of functionality in 5, both visible and under the hood, that you wouldn't necessarily see.
Under the hood.
But it's pretty, yeah, Sketchpad 5 is pretty amazing. Definitely worth it.
Okay,
right, well,
I think we're going to end it
for
now.
Joining us. Yep, thank you for joining us this evening or afternoon, as the case may be. I see we got a lot of people on still, but
yeah, I'm going to close it. So there's a quick survey. There's a quick survey that follows. Just give us some feedback. We love to get your feedback. We do try to make sure we're keeping these up to date. So please answer the survey questions real quick, and just so we can improve these. And hope to see you next time. Thank you. All right, I'm definitely ending it now. Good night, everybody. Good night, Gracie.